that happen?
They strung it up on like the system. I don't know.
How do you get the order?
Is the projector on?
How do you turn it on? Oh yeah, the other thing is about the audio pattern.
Excellent signage.
Yeah, how does this happen? Well done. Excellent.
You know, like us putting the sign, just the retort, because they got fancy mics.
How do you figure out like whether this is actually cool? Yeah, it looks good, right? Alex, do you think this thing's working? Hello, hello.
Sit down.
Oh, streaming on OBS.com.
Oh, wait. What? You just renamed it. Why the hell did you know? Oh, maybe fine. Who cares? Let's just start.
As in just like do this.
I think we. Oh. It's internal computer.
Hello.
Yeah, there you go.
Oh, okay. Thank you. I guess this is like our microphone, by the way. Oh yeah, this works. It is a bit too high for these streams, so I mean we can set it down like this. I think it's reasonable. Hi everyone. Before we start, could everyone try and scan the attendance form? Just so we can get food to you guys. There's quite a lot of people today, so.
Guys, lock in. It's time to lock in and scan the attendance form. Please. Otherwise you don't get food. And if you don't get food, I don't get food. And that's the main reason I'm here. So if you've liked me at all this term, please scan the attendance form. Please. Thank you.
Great job.
If you haven't liked me, please don't say anything. 1511, so I hope you're not there.
Yeah, okay.
Susan, yeah, you. What are you trying to do? What's the introduction?
Okay, so we'll give you guys some time to fill that in at the end of the workshop as well. Today, we have some problem sets online. So like if you guys know what BFS DFS are, if you want to get some practice in, you can go to this link, and this link has a couple of problems. I do suggest you guys actually practice doing this. Do be aware that like any ADTs or whatever that you might want to use, you will have to write them yourself. There's no like provided ADTs. So you could do like these problems if you're familiar with C++ as well. Alternatively, you can just like do whatever problems I think 2521 has.
Two things. First of all, you do want to practice BFS and DFS. That is not a question. I don't care if you're confident or not. If you're confident or not, you do want to practice it. Second of all, the ADTs, I pushed the lecture code after I had my lunch today. So the ADTs that you might need to solve these problems are available on the course website for Comp 2521. So much like in the exam, writing the ADTs is not going to be a restriction for you. And if I see anyone not practicing, I'm going to be really upset.
Yeah, keep in mind that C++ code compiles exactly like C code with some like it's relevant details. So yeah, you guys can just like select C++ as your submission language. It should work if you just send in C as well. Okay, so I guess we'll get started with content. Oh, okay, sure.
Also, the main reason I've shown up is just to say I highly recommend all of you come here, but I am required to say that this is not an official 2521 workshop sponsored by me. I've not reviewed any of the content they've done. I know the people here. I'm sure they are amazing and it will be excellent, but if you want to yell at someone, it's not me.
That's all. I just had to say that.
Okay, thanks.
If you want to yell at someone, yell at Austin. But we'll get started. Okay, so we'll go from the very basics. What is a graph? A graph is made up of nodes and edges. So a node, also known as vertices, they just represent entities in the graph. Edges represent the relationships between these entities. So these can be directed, so a one-way relationship, or they can be undirected. And on weighted graphs, each edge has some cost. And I'm sure you're all familiar with most of this, but some examples are cities connected by roads, game states, which is a bit more of an abstract type of graph, and the human nervous system for fun. So yeah, here are some examples. The first one is like a map, which lends itself pretty well to a graph representation, and the second one is the game states of tic-tac-toe, so you can see how each state is connected by edges. Yeah. Some more definitions. Two nodes are neighbors or adjacent if there's at least one edge connecting them. A path on the graph is a sequence of nodes where each pair of adjacent nodes are neighbors, and a cycle is just a path that starts and ends at the same node. And here is a very simple graph. We have a valid path A, D, E, B, and then a cycle, which is D, B, E, D, and then this one is not a valid path because A and E are not directly connected. Okay. So how do we represent these kind of structures in code? So there are three main ways. The first way is an adjacency list. So for every node, we simply store its direct neighbors, and this is a very common representation method. The second way is an adjacency matrix. So this is kind of like a grid. The value of each cell is going to be 1 if there's a path from the vertex that's labeled like by the row and the column. And this will be more clear in the next slide where I have a couple of pictures. If the graph is weighted, then the cell can store the weight instead. The last one is an edge list, which is just a list of all of the edges, and it's not too useful for beginner problems in graphs in competitive programming. Yeah, so any questions so far? I know I kind of went pretty quick over the basics, but that's because I'm sure you're all very smart from 2521. I'm sure Henry did a good job.
I actually wasn't here when we taught graphs.
Oh, okay, great. Okay, so here is a diagram of what an adjacency list looks like. So for each vertex, for example 0, it is connected to 1 and 2. So it corresponds to this list of numbers 1 and 2. For node 4, it's connected to 2, 3, and 5, and you can see that here. This diagram is from Visual Algo. It's a pretty good website. You should check that out as well. The second way is the adjacency matrix. So what this, for each cell, it has like a corresponding row and column number, right? If that number is a 1, then that means this number here, this row is connected to like that column. So for example, 2 and 4, there is an edge between them. So if you go to row 2, column 4, it's marked 1 as there is an edge. If there's no edge, like between 2 and 6, then it's just marked 0. Is everyone happy with that? Yes? Okay. So which method should we choose from these two? Well, they each have their pros and cons. So for the adjacency matrix, because we have to store such a big grid of cells and some of the entries might be 0, it's like there is some space that's wasted. So no matter how your graph is connected, it's always going to be v squared, even if there's like a node that's not connected to anything else. For your adjacency list, it's a bit more efficient because we only store the necessary edges. So if you have like a graph that's got a lot of nodes and not that many edges, it doesn't waste too much space. The benefit of an adjacency matrix, however, is that you can look up whether an edge exists in O of 1 time. So if I go back here, it's pretty easy to straight away say if there's an edge between 2 and 4. You just have to look up the corresponding cell. For the adjacency list, this is a bit harder for your computer to do because you get a list of numbers and you're essentially just trying to find if the neighbor exists in that list. So for example, if I want to see if 2 is connected to 6, I have to look through this list here to find if 6 exists in there. So that is a tad bit slower. But to loop through all neighbors for the adjacency matrix, you have to go through the entire row in a matrix to check if an entry is 1 or 0. Whereas for the adjacency list, you have the list of neighbors directly. So in most beginner graph problems, the adjacency list is good enough. Sometimes we also have implicit graphs. For example, you might have a problem on the grid, and maybe you can only move like cardinal directions. In that case, you don't really have to store the neighbors of each node. It's just like north, south, east, west. But I don't think we cover that in too much detail here. Okay, on to Austin, the main person you guys should get at.
Questions about any of the content that we've covered so far? Yeah, sure.
So you said we either use adjacency lists or matrices.
Yep, that's true.
Yes, he said that.
Okay, bye, Susan. Yeah?
You described all the benefits of using an adjacency list.
Yep.
Are there any problems for which we like to use a matrix instead?
Wait, like, didn't Susan just say, like, you can find the edge in O of 1? So, like, like, if you wanted to find an edge, you can do it really quickly, right? Like, say there's like Q queries and Q is on order n squared, then you can, like, do it in O of n squared, as opposed to, like, yeah? Oh, okay. Yeah, like you can do it in order n squared, right? Like to answer all the queries, right? But like, for example, like if you had n squared queries and then like you needed to loop through all the neighbors, it'd be like O of n cubed, right? Like, okay, pretty artificial question, but sure. Yeah. Yeah, sure. Not at the moment. That is a good question. If, for example, yes, thank you. You're welcome. Okay, so in this case, if we were to include weights on edges, the best thing we would do is in our adjacency list, instead of storing just a single number, we could store the node and also a weight of that edge, right? So we store like a pair instead of just a single integer. Does that make sense? Yep.
Sydney, if you're plugging this in C and you don't have access to the pair, how will you do it in C?
Who knows? Yeah, okay, fine. Yeah, you can use a struct, right? Like, does everyone know like structs in C, right? You can just write a custom struct to take in, for example, a node and also like a weight. Does that make sense? Yeah. And then like you just build your like. I assume you won't have to implement a JC list from scratch, but if you would have to do that, like you'd probably just like create a linked list and then like all of your nodes or all of your values are just like that struct instead of like just an integer. Does that make sense? To everyone? Yep. Sure. Great. So we'll move on to sort of the main part of this lecture. And so I'll be looking at basically how to explore a graph, right? And so you might have seen, you might have some idea of how to do this already from 2521. But let's start with, I guess, like a definition of this thing called connectivity, right? So we can say that a node U is connected to a node V if and only if one can take a sequence of edges from U to V, right? In that case, U is connected to V. And in an undirected graph, if basically a maximal set of pairwise connected nodes is referred to as a connected component. It's like a very wordy definition. What it just means is like you take a group of nodes, and those nodes all have to be able to reach each other, right? And then basically the idea is if you add another node, then that node will like fail that condition. So you won't be able to have that node reach every other node in that group. So I guess like we could look like a visualization. This is like an example of a graph. And in this case, there are 3 connected components. It's very easy to spot visually what they are. You've got this red one here. That's a connected component because every node inside there, if you pick 2 nodes from red, you're able to make a path from one to the other, right, by taking a sequence of edges. Likewise, for green, sorry, that's not green, blue, you're able to do the same thing. And for purple, you're able to do the same thing. A single disconnected node is counted as its own component. Does that make sense to everyone? Yep. And I mean, we can consider this problem, which I had. It's called making friends. Basically, there are n people, and m pairs of these people are friends. So every time you see like n and m, or like v and e in a problem, you should think of a graph, right? Like this is like a very like meta hack to solving graph problems or identifying whether a problem is a graph. You just look for like the common letters, right? Like n vertices and m edges, or like v vertices and e edges. I guess like the actual way you would identify that this is a graph is to notice that you've got some number of people, and there are like some pairs of people being friends. Usually when you see pairs of something, you would think edges, right? Edges between 2 nodes. And so in this problem, rumor is spread between friends. And my question is, if person 1 has a rumor, who will it spread to? So for example, in this particular example, say that I injected a rumor at person 1, then it would spread to 2 and 3, and 4 and 5. Right? Does that make sense? It would not spread to like this group of friends because like nobody knows anyone from group 1. Does that make sense to everyone? So, how can we solve this problem? Firstly, we can't just consider the adjacent nodes, right? Like for example, we can't just say like, it'll spread to 1 and 2 and that's it. Sorry, it'll spread to like 2 and 3 and that's it. So we need to do a bit better than just like looking at adjacencies. So in particular, we need to find whether a node is reachable from another. So in other words, we're trying to find the nodes which are in the same connected component as node 1. So how can we do this? Well, let's simulate how a rumor spreads, right? And maybe the easiest way to do that is say that the rumor lives at node 1 first. What we're going to do is these, I guess like these yellow nodes will mean like the rumor is about to spread to that node. And then I'll have blue nodes represent like the rumor is already spread to those nodes. So in this first case, this node, the rumor is about to spread, and let's say we inject it. When we inject it, the rumor spreads to all the adjacent nodes, 2 and 3, right? And then in the next move, 2 and 3 spread to all the adjacencies. In this case, it's 4. And then 4 finally gets the rumor and spreads it to the only final, neighbor 5. And then 5 gets the rumor. So does everyone understand this sort of like simulation? Yep. So we visit all the nodes at the same distance together, right? If you think about what this traversal does, it visits all the nodes of distance 1, and then all the nodes of distance 2, and then etc. Yeah? And so this traversal, we call breadth first search. And the idea is like we traverse the entire width first, so we're traversing the breadth first before we do the depth, right? So we make sure everything of the same distance or the same depth is covered before we move on. Does that make sense to everyone? Yep. So you would have studied this in 2521 if you do the course. I assume a large majority of you guys are here because you do the course, correct? Yeah. Okay. So to formalize what happens in BFS is we start at some starting node. In this case, we set it to be 1. And then we keep a set queue of nodes in our current layer. Right? The way I'm going to introduce this might look a bit different to how you learnt it in 2521, but I'll explain what these similarities are. So we first keep a set queue of nodes in our current layer. Then the first thing we do is we visit every single one of the nodes in queue. Yeah? And as we do so, we extend the boundary by peeking at any unpeaked neighbors. So if you think about like visiting as like those blue nodes and peeking as those like yellow nodes, what we're basically doing is saying if we haven't already peeked at it, then we should peek it and place it in some new set, right? And let's call this new set Q prime. Then what we're going to do is, after everything in Q has been visited, we're going to replace Q with Q prime. So in this way, what we're basically doing is we store like two lists, or like two, whatever linked lists, I don't really care. And the idea is, our current list contains like all the nodes which we are going to visit in this iteration. And so we're going to visit all of them. And as we visit all of them, we're going to successively append the sort of like the next iteration's nodes to the new list. Yeah, and at the very end, we're going to replace the new list, or we're going to place our original list with our new list. So basically saying, okay, we've finished all the nodes here. Now let's look at the next layer, which is like the new list, right? And so we keep going until there are no new elements to explore, right? Q prime is like the list of nodes which haven't yet been explored. And so if Q prime is empty, that means we're finished exploring the graph. So what's the time complexity of this implementation of BFS? Does anyone? Yeah? Vertices plus edges. Was that what you were going to say as well? Yeah, V plus E. Does anyone else have like another guess to the time complexity? I mean, like, you guys all learned BFS. We visit at most n nodes, and at each node we peek at all its neighbors, right? That should not be apostrophe, sorry, my bad. So over the entire traversal, we peek at 2m nodes, and so it's O of n plus m, right? Where n is the number of nodes and m is the number of edges, right? Does anyone have any questions about this? Okay, sure. So the way that BFS is implemented is not usually with two arrays, or like two lists that we successfully replace. It's typically implemented with a queue, right? And in here, elements of Q prime they're directly appended to the end of Q. And then elements of Q are popped off from the front, right? So you've got some Q, and then every time you want to add a new element, you just add it to the end, right? Because you're going to process it after. And then every time you successfully process an element, you pop it off from the front, right? So in this way, we're maintaining like that same Q and then Q prime order, but just with one list instead, or like one linked list instead. Does that make sense to everyone? Yeah. And so it gives us the exact same time complexity, but it's like a lot easier. Okay, so I was going to do demo stuff or like implementation, so I guess I'll do that.
Hey, hopefully you guys can all hear me. I'm going to speak a bit louder. So I'm working in C++ here, so it is a bit annoying. Can you guys see the screen now? Is it like visible? You guys can, there's also a screen like on each individual person's desk. This room is rather fancy, so yeah, so you can look at that. So basically the idea behind BFS is what we're going to do is we need some Q to maintain the elements. And I mean, like, you've heard of how you've heard of like how Susan explained to show graphs, right? Or like to represent graphs in code. Typically we use something called a adjacency list. And what this looks like is an array of linked lists, right? And so in C++, the linked list is called a vector. And so they've implemented linked lists for us. We don't have to write all of the thing. And it is we can call it like, I don't know, some like array of size max n. You're gonna like double check my thing. Yeah. And so this adjacency list this adjacency list basically stores like for each basically edge I stores the list of all the nodes which are adjacent to I, which I can reach, right? Which I can reach in one step. Does that make sense? So that's our adjacency list. And so I'm not going to worry about populating that for now in the main function. What I'm going to worry about is how we actually implement our BFS, assuming this list is full of its elements already. And so what we're going to do is, firstly, we're going to write a function, like let's just call BFS, and let's give it like a starting node. In this case, let's set the starting node to be 1, right? And so the first thing we're going to do is we're going to use a queue, right? And so in your actual course, you'll probably, if you ever have to implement BFS, you'll get like an ADT from a queue, like queue.h header or whatever. In C++, we're in like C++, not C, so they actually have like a self or like a already pre-done implementation. This is why I like C++. But yeah, they already have an implementation of this structure for us. And so we can call things like queue.front, and then like q.push, and then like q.pop. So these are like the available functions for us. So the first thing we're going to do is add s, our starting node, to our queue, right? And so what we're going to do is we're going to push s into our starting node, right? And so what this queue represents is basically all the nodes which we want to visit. Yeah? So while the queue is not empty, which means there's still, huh? I don't care. So while queue is not empty, that means we still have nodes that we want to process. Yeah? And so what we're gonna do is, firstly, we want to figure out which nodes we've already processed. We can store like a viz array for this. Sure. Okay, like you can just like do it, right? So here we go. We've got like a viz array. This represents like whether or not we've seen a node. And then so while the queue is, let's just set this to this. Set this to 1, meaning we've pushed it in. So while the queue is not empty, firstly, if so we're gonna get like the top node, which is like the next node we want to visit. What am I doing? Yep. And then, okay, so sorry, I didn't do 1511, so I don't know like the C style crap. Okay, so okay, here is basically we're taking the node from the top of the queue, yeah, and then we're gonna remove it from the queue, yeah. And then if we've visited it, which should never happen, we should just continue, right? Yeah. Okay, well, whatever. I don't care. Okay, so we're gonna loop through all the adjacent nodes in this U, right? And I guess we can call it V. So we're gonna look at all the nodes which are adjacent to V. And this, like, is this a valid syntax in C?
No, it's not.
Okay, so okay, this just means we're looking at. Okay, do you know what? I'm gonna do.
We'll write it as a C for like
Yeah. Yeah, so we're going to look at basically all of the, we're going to loop through the indices, and we're going to basically set our V to be like add UV, right? So this is the, this is like one of the neighbors of U. And so if we've visited this neighbor, we should not process it again. We should not put it back in our queue, right? Otherwise, we do need to chuck in our queue. So what we're going to do is firstly, we're going to mark it as, hey, I've visited it, right? I've chucked in my queue. I'm going to actually chuck in my queue. And then I'm done, right? That's it. So this is what I do. And at the end, like we're done, right? We should have visited everything that we can. That's it. Yeah? Yep. AJU.size. This is a built-in. This is like a built-in thing for vector. So vector is basically a linked list, and so dot size on a linked list gives you like the number of elements in that linked list. Yeah. Yep. Yeah. So this is like a detail. In like for BFS, when we push a node into the queue, we know that we don't need to push a copy of that node back into the queue, right? This differs from like, I don't know, like you've heard of Dijkstra, right? So it differs from Dijkstra. So when in BFS, if you push it in the queue, you don't have to push it in the queue again. So we can just mark it as visited then, right? So, yep.
I think the idea is like in BFS, the first time you, I think, peek at a node, that is the shortest distance it will ever be. Whereas in Dijkstra, sometimes you might peek at it once, but it might be far away, and then later you could get to a better distance. In BFS, we can just do this now. It's a bit easier.
Yeah, like what you can do is you can have this go here, and then this would be like the same.
You put this V.
You'd put like
Just shift that up.
you just do it.
If you're more familiar with Dijkstra, this might look more familiar, but they both do the same thing, practically.
So does anyone have questions about this particular implementation? I know that I've used some, I know I've used some like C++ specific things, but like I've tried to like, I guess like boil it down for you. This vector is just like a linked list, and you'll probably get this in the exam. And likewise, this queue is just like a queue implementation. They usually give this to you as a header file. Yeah? Yep. Okay. And so I won't bother like testing this code. Like I'm fairly certain it's correct. So if we don't have any questions, we'll move on. We do have like quite a bit of content to cover. So why do we use BFS? And I think this is like this is possibly like one of the more important things to know, which is like in the exam, when should you use certain like traversal algorithms, right? And so there's one key property of BFS which makes it useful. if you consider all the nodes which are distance d from S, they're all visited before like d plus 1. So what this means is that the first time we visit a node is actually the earliest that we'll ever get to it. So in short, this basically visits a node as quickly as possible. So for example, say you were trying to find the shortest path from, I don't know, S to T. You can just BFS from S, and then the first time that it reaches T will be the earliest or the shortest time that it will take to reach T. Does that make sense? So the way that BFS works is it processes all the layers one by one, right? Like it processes layer 1, and then layer 2, and then layer 3, etc. So the first time it will hit a node is actually the earliest, because every subsequent time will be later, right? By definition of BFS. So BFS basically greedily chooses all the nodes in reach, and because it knows like no path that it can find in the future can beat it. And so this is an important property, and we actually want to keep this in mind for some future algorithm, right? But there's like another strategy that we can use, and you guys will be aware of the strategy as well. And so say you have a graph now, instead of like, spreading it out, let's just like try go all the way, right? Let's see like how far can this rumor spread until it can't spread anymore. So, let's say it spreads all the way around here, and now it can't spread to any more unvisited nodes, right? And so it's going to backtrack. And it's going to reach 4, and it's going to spread to 5, and it's going to backtrack all the way back to 1. Yeah? And so now the entire thing has been visited. 1 is the starting thing. It's going to stop spreading. And so in this traversal algorithm, we basically walk the graph like a maze, right? So we basically go to the very end, and then once we get to the very end, we start moving backwards to try earlier branching paths, right? Like for example, here, we didn't try one of these paths. We just went down one of them, and then we eventually went back once we hit the dead end to explore the other path, right? And so in this case, since we're searching all the way down, we're basically prioritizing depth, and so we call this depth first search. Does anyone have any questions about any of this? Yep. It does the, you can do it in any order. So for example, I could have equivalently gone from 1 to 4, 5, right? This is fine. I just went to 3 because I thought it was like a decent convention. Yep. Yes, for unweighted graphs, BFS guarantees the shortest path from. DFS does not, and because it explores all the way down, right? So the key difference between BFS and DFS is BFS explores all the layers one by one, right? That means the first time it hits a node will be the earliest it can hit, right? But that's not necessarily true of DFS. I think the easiest example is, in this case, we hit 3 after 3 moves, right? But we could have alternatively hit 3 after just 1. Yeah. So let's formalize what this algorithm actually does. So in this algorithm, DFS, we start with some node s equals 1, and as we process our current node u, firstly we mark it as visited, right? This means it's like processing, and then we visit some unvisited neighbor by recursively entering it, right? I'm going to be doing the recursive implementation. I feel like this is like a lot easier than just using a stack. To be fair, a stack is just like functions anyway, so it doesn't really matter, right? Like you refer to the functions as I do not believe so. I think like when I did the the supplementary, they were just like do whatever you want. We'll give you a queue, we'll give you a stack if you want to use BFS or DFS, but there's no like requirement to necessarily have to use them. Yep. Yeah, exactly, right? Yeah. The way that function calls operate is basically like a stack anyway, right? Like you call one function and you call another function on top, and then those functions get successfully popped off. Yep. Because that's a good question. BFS processes nodes in something called queue order, right? So if you remember when we did BFS, we processed the nodes in like this order where when we add them, like the first time we add them is the first time that we'll process them. Yeah, the earlier we add them, the earlier we process them. DFS does something called stack order, right? Where it's the last thing that we add is the first we process. And so for DFS, we are able to do it recursively because function calls behave like a stack. right? So when you call functions, they successfully get added to like your stack, right? And then as you exit out of functions, they like get slowly popped off the stack. Yeah. So this is basically how function calls act. We can just like use that as an implicit stack in order for us to do our DFS. Yeah. So we can't do that for BFS because stacks don't act like functions don't act as queues, right? So in this like DFS process, just to continue, so basically we have some node U, and we're going to visit like some unvisited neighbor, yet unvisited, by recursively entering V, and then we're going to say explore, continue exploring V, right? And so we will do whatever, right, in V, but when we return from V, we'll just continue dealing with the remaining neighbors of U. So what it will look like is basically, for each neighbor of U that's not yet visited, we're going to basically call this function recursively, say continue exploring at this neighbor, and then basically the neighbor will do its own exploring thing, and then at the end it will come back and say, hey, I explored everything that's connected to me. And then you will say, okay, great, let me try my other neighbors. Yeah? And so basically what this recursive thing is doing is basically offloading the work to each neighbor. Basically saying, as me, I'm just going to say, basically I've got the task to explore everything which I'm connected to. I'm going to tell one of my neighbors, hey, you explore everything you're connected to. Right? And then when they come back and they say, hey, I've done it, then I'll say, okay, my next neighbor, go explore everything which I'm connected to. Does that make sense? So you're basically offloading the work and you're shouting at your neighbors to do the work for you, right? Very realistic, right? And then once everything adjacent to you is visited, then we'll exit from you. That's pretty much the algorithm. And so you guys will already know this, but as revision, what is the time complexity of this implementation of DFS? Yep. Does anyone else want to disagree with this claim? Okay, like nobody, right? So in this case, it's like the same analysis. We visit at most end nodes, and we traverse each edge at most twice, right? Every time we move forward, we traverse that edge, and when we return back, we traverse that edge again, right? So it's basically 2m like edges we traverse, and then at most end nodes, so it's n plus 2m, which is n plus m. Yeah? So this is the time complexity of DFS. And so DFS has like two key properties that make it useful. Firstly, it's really fast to implement if you don't care about the order which you visit things. So BFS, you want to visit things in layer order, right? You want to visit all the smaller or the closer nodes before you visit the further nodes, right? So that you can do shortest path. But for DFS, if you don't really care about shortest path, you just want to visit everything, it's actually really fast to implement, right? And it does the same job, right? It visits everything. So in an exam, typically what I would give the advice for is like if you need to compute the shortest path on some unweighted graph, I suggest use BFS. But if you only need to care about things like reachability or like connected components or like whether something is visited, able to be visited from something else, then you should use DFS. It's a lot faster to implement. And there's another interesting property regarding like spanning trees formed by DFS traversals, but we're not going to go through that. It's like not part of 2521, right? So I'll showcase the first property, which is like being really fast to implement, right? Okay, so in this scenario, I've already implemented BFS. And BFS, as you can see, it's not too long, but it is quite quite a hassle, right, to implement. You do need to create a queue, you need to push things, you need to make a while loop, you need to visit things. Let me show you what DFS looks like. So DFS is also a void function, right? It doesn't need to return anything. And it takes basically what current node we're at, and let's call this V. Yeah? And so for DFS, the default value for V should be 1, right? We should start at 1. Then, firstly, if we've visited V, terrible idea. First, we're going to set V to be visited, right? So what this means is our current node, we're going to mark it as visited. And then what we're going to do is we're going to loop through all the adjacent neighbors of V. And I'm going to do like basically boilerplate, like I'm going to just copy exactly what I wrote on top. So V is the adjacency of UI, right? So this is our, terrible idea. I should switch it around. Okay, so in this case, U is the neighbor, right, of V. And then, so now I've got a U. This is like a loop that grabs all the neighbors of V. And then, if I visited U, then what do? I should continue, right? I should not recursively call that DFS. We've already visited it, right? But if we haven't visited it, we should just tell U, hey, visit all my stuff. And this is the end of the BFS. So that was like a lot less painful than implementing the BFS. And as you can see, it's like significantly less lines as well. And so a recursive implementation of DFS is actually extremely quick to do in contest. I believe like if you get enough practice in, I do believe that you can code a DFS up in probably 15 seconds in the contest or like in the actual exam. So I do believe that all of you are capable of doing this. And so the reason like why it's so fast is because like, I don't know, we don't have to do all this queue garbage, right? And we don't have to use their ADTs, right? We can just like write a recursive function. So if you can't be bothered like looking through the CPP file or like the C files to try and find what methods you're allowed to use, you can just write DFS, right? It's very quick. So the thing about any questions about this particular traversal algorithm. So I'd use this one in most scenarios. I'd use BFS when I need to find the shortest path. Any questions? Okay. I think everyone knows what's going on. So now I'll actually explicitly go through some shortest path algorithms. So, like we said, we already know how to find the shortest path between A and B on an unweighted graph, right? How do we do that? Does anyone have an idea? Say we want to find the shortest path from A to B on an unweighted graph. How might we do this? BFS, right? So BFS starting from where? Starting from A, right? So we should start from A, and the first time we reach B should just be like the earliest time that we can reach B, therefore the shortest path, right? So the first time we reach B is therefore the like I guess the shortest path to B. So in this section we won't be looking at unweighted graphs. We know that for unweighted graphs we can just BFS from A and reach B, right? The first time we reach B will be the shortest path. So instead we'll be looking at weighted graphs, and in particular these weights will be non-equal and non-negative. So the reason why we are saying the weights will be non-equal is because think about like what happens in the case that all the weights are some fixed constant like 10. Yeah, it's basically unweighted, right? Exactly. So what we can do is we can just treat it as unweighted and multiply the final answer by 10, right? All the edge weights are the same. We can just divide the entire graph by 10, and then we just like run BFS, and then we multiply it by 10 at the end to recover the original cost. The reason why we make them non-negative, it will be obvious to those who have done the course. Yeah, okay, I'll leave it at that. So, minimum cost paths. So, okay, I like, anyone who was here in previous workshops will remember this particular character. If you don't, so this guy is called Rob the Racist, right? So, Rob is exercising his favorite hobby, which is racing, right? Like, Rob is a racist, he really likes racing, right? So, basically, before he picked an array, now he's basically picked a race course to run on with n intersections and m bidirectional paths between them, right? And so if you can think about this as a graph, that's already very helpful, right? So once you read this, you should immediately be thinking this is a graph problem. You've got n intersections and you've got some paths between them, right? And basically his job is he starts at 1 and he needs to run all the way to n, okay? Unfortunately, Rob also happens to be exercising his second favorite hobby, right? Which is being racist. So the ith path contains some number of undesirables, and let's call this like wi, right? So each road contains some number of like undesirables he doesn't want to meet. And so if Rob runs along path I, he'll encounter all wi people. And so my question is, help Rob find the minimum number of undesirables he needs to encounter on his race. And I mean, we'll give some constraints. This is like a typical constraint that you might see in an exam or in a contest. Obviously, you may not get this exact flavoring of the problem in contest. I think there might be some issues, but you know, whatever, right? So, does anyone have any thoughts about this problem? Or like, how might we solve it? Yeah? Nearly, yeah. Not exactly. I think MSTs is a good idea, but I think like basically the question is not to form a tree. The question is like you want to just run from 1 to n with the minimum cost path. Yeah. So So most people are saying Dijkstra. What we're going to do in this section is I'm going to provide a sort of like intuitive rederivation of Dijkstra. So like how might we rederive Dijkstra algorithm, right? So this is, for example, an example of the problem. So in this case, you've got like a bunch of roads. For example, this road has like 7 people that Rob doesn't want to meet, right? And then here has like 2 people, etc. And then basically what Bob wants to do is run from 1 to 6, right? And then so turns out he can't just run directly because that is a cost of 7. So if you were to BFS, for instance, you'd hit this 6. It would be like not optimal, right? Instead, you actually want to take this path, which is like, Bob really wants to go out of his way to not meet these people, I guess. Like he'll run this entire circular track to meet 6 people instead of meeting 7 people. Yeah? So does this make sense, everyone? Yep. So we know how to solve the problem when the graph is unweighted, right? Using BFS. So let's try and construct an unweighted graph from this. And what I mean by this is basically, say that we have an edge from some node to some other node with a cost of, I don't know, like 3 or something. What we can do is basically replace it with some unweighted edges, like this, right? So we're going to create like fake nodes, and then the fake nodes are going to sit between the 2 vertices. And then like let's call them A and B. And then so in this case, each of these edges are weight 1, right? Together, they make up a weight 3 edge, right? So to get from 1 to 2, it's still a cost of 3. We've just turned this edge into like 3 unweighted edges. Yeah? And so we can do this for the entire graph, right? And so now that our graph is unweighted, we can just run BFS on it. And I guess like an example of like how we could do this for an entire graph. In this case, we've basically taken the path from 1 to 2. And we've converted it into this really long path with 2 extra edges, 2 extra nodes, right? And then similarly from 2 to 4, like we've basically created another like splitting, right? And then from 1 to 3, we've done the same thing, right? From 1 all the way to 3, we've basically turned this into a length 4 path, right? 1, 2, 3, 4. And then from 3 to 5, since it's only length 1, we can just replace that or represent it with a singular edge with no added nodes. Does this make sense? Like how we're deconstructing the graph. So, what's the time complexity of this operation of BFS? Well, now, since all the edge weights are like 10 to the 5, 10 to the 9, which is like 1 billion, now we have like 1 billion M nodes. So it's like a bit slow, right? It's like O of 1 billion M. So I'm not sure if you guys learned like how to estimate runtime of a I guess like a function or I guess like a program. But like roughly this number in here needs to be like I don't know, like 100 or like 1 million or 10 million. It can't be any bigger than 10 million. So this is 1 billion M. So it might be a bit slow. So how are we going to speed it up? Well, if you think about like the path from 1 to 2, we don't actually care about like these intermediate nodes, right? We only put them there so we can run BFS on them. But we don't actually care like how like when we actually get to them, right? Or to get to these intermediate nodes. So we actually only care about the order which the purple vertices are visited, right? So for example, if this one is visited before this one, then we know that this one is a shorter distance from this one, right? So what is this order? Well, it turns out our BFS visits all the nodes with distance d before those with distance d plus 1, right? We covered this when we talked about BFS. And so our current closest node will always be visited first. So basically, since we visit all the nodes with distance d before distance d plus 1, our closest nodes, those with distance d, will always be visited first. So what that means is, for example, in this case, 2 is a distance 3 away, and 3 is a distance 4 away, which means 2 will actually be visited first. Yeah? And then 3 will be visited because it's of distance 4. And then 5 will be visited because it's of distance 5. And then 4 will be visited because it's of distance 6, right? So we visit, because of this natural BFS order, we're actually visiting all the purple nodes in order of closest distance from source, right? And so we basically visit greedily based on our distance from S. So at each point, basically what we're doing is just pick the closest node found so far to process. So instead of processing all the white nodes, the intermediate nodes, we don't actually care because there are no choices, interesting choices to be made here, right? There may be interesting choices at the purple nodes where the graph actually branches, right? And so what we're just going to do is we're just going to accelerate the process of BFS by instead of like sort of manually going step 1, step 2, and then whatever. We just like instead just pick the greedily closest node to process, right? This is basically simulates the exact same thing as BFS, but we don't care about advancing like all these intermediate nodes. Does this make sense? It's like a slightly more complicated, I guess, algorithm. And so let's consider this algorithm. I'll call it like BFS++. And the idea is we start at some starting node, S equals 1, and then we keep a set of nodes Q. And in this time, not only do we have to keep a set of nodes Q, we also have to maintain the best distance for each node, or like the closest distance from each node to the source. So what we're going to do is we're going to visit nodes, and the order which we visit them is we're going to pick the smallest distance node first. Yeah? And then what we're going to do is, when we're at that node, we're going to extend the boundary, and we're going to peek at any unvisited neighbors of V. Right? So we're going to do the same thing as BFS. We're just going to look at all the neighbors that have not been visited, but we're going to peek at them if they haven't been visited. So we know that things are visited if we've cemented them, we've actually like gone in and processed them. Like if they are in the queue, they are still unvisited. We still need to peek at them just to check, right? And so if we found a better distance, we should update, and otherwise we should insert it into this queue prime. And then after everything in queue has been visited, we should replace queue with queue prime. So it's very similar to this old BFS. And so we keep going until queue prime is empty. My question is, what is the time complexity of this algorithm? And maybe I won't ask you guys. Instead, I will move on to the slide where I spoil the reveal, which is like, we just rederived Dijkstra's algorithm, right? Like the algorithm which I mentioned here, where you visit all the nodes by picking the smallest distance node, and then you advance them, and then you update the distances. This is just Dijkstra's algorithm. Yeah? So Dijkstra's algorithm is basically BFS, but we have this new check where we just pick the smallest distance node, and we have to update the distances. Yeah? And so the time complexity of this algorithm actually depends on how quickly we can find this minimum distance node in queue. So the really crucial point here is that we're like picking the smallest distance node greedily. So it actually depends on like how fast we can do this. And so how fast can we do this? Well, we can do this however fast we set queue to be in terms of a data structure, right? So often we can use something like a heap or a priority queue in order to do this operation. And why do we choose these? Well, I mean, in C++, it's called a priority queue. You have learned them as heaps. And they can be thought of basically as a queue, but it maintains all the elements in sorted order. So it's like it's the same thing as a queue, but it just sorts all the elements as you insert them in. And insertion and removal of the minimum element are both log n in a heap, right? Probably. So instead of searching through queue manually, we should just replace it with a priority queue, right? And so what this will look like is basically, instead of just chucking the nodes in, we basically chuck this pair of things in. And we basically force the heap to sort based on this first element. So in C, you would use like a struct pair, like you would like define your own struct to hold two elements, and then force your heap to compare based on this first element, the distance, right? And then so whenever we update the distance, we should just push this new distance in. And then since the current distance or the new distance is always less than the old distance, we'll always process the most updated version first. So we can have a bunch of copies of U just living inside Q, but the crucial point is the best copy of of U will always get processed first. We'll always extract that out of the heap first, right? Because it's like a min heap, we care about the minimum distance. So the best option for for U will always be extracted before the other copies, which are like less good. Does that make sense to everyone? Sure. Okay. And so if we extract a node that we've already visited, we skip over it. So once we extract a node that we've already visited, we don't need to process it. It's the same as in BFS. We just skip over it. And so it's the same as BFS complexity, but we've incurred an extra log factor from using this heap and priority queue to find the minimum node, right, from queue. Oh yeah, food's here. You guys should get food. Huh? Fine. Okay. Okay. Let me implement Dijkstra, and then you guys can have some food. So, Dijkstra. I'm gonna start shouting again because I really don't want to hold the microphone and speak it. Okay, so for this algorithm, which is Dijkstra's algorithm, what we're actually going to do is we're just going to copy paste the BFS implementation, right? And the reason why is very simple. It's because Dijkstra is based off BFS, right? It's basically the same as BFS. So instead of calling this BFS, we're going to call it like Dijkstra, right? And so instead of using this queue, we'll use a heap, right? And in C++, in C++, this is a min heap is implemented using something called a priority queue. And there's a lot of complicated things going in here, but this basically implements a min heap. That's all we care about. And so what we're going to do is we're going to do the same thing. We're going to push S. We're not just going to push S, we're going to push a pair. So in C, you would have to write your own struct for this. In this case, the distance of S is 0, so we're going to push that. In fact, I should probably make a distance array. And then we're going to also set all the values in distance to some really big number, and that's what this line of code does. So everything in dist is like infinity except for S, which will be set to 0. And so while we've still got elements in our priority queue, as in while we still need to search for things, we're basically going to get the best node, and we're gonna just get the node itself. So this is the node, and so if viz of this node is true, then we're going to continue. Otherwise, we're going to set this thing to be 1. We've visited it. And then we're going to pop it from our queue. Then we're going to look at all the adjacencies of view. We're going to look at this, all the neighbors. And crucially, we're not going to just push it arbitrarily.
Above the continue, please. Because it's going to...
Oh, yeah, true.
Also, why are you doing structured by other? You do see stuff all you're doing structured by.
Okay. Okay, so I've gotten complaints that I shouldn't be doing that. Fine. I guess I'll do this. So boring. Okay, so basically the idea is inside here.
Your priority queue isn't even pairs, bro. It's just
Okay, true. Factually correct. So what we're going to do now is don't worry about what I'm doing. Don't worry about it. So, what we're going to do now is we're going to basically check, not only do we have to check whether it's been visited, but we also have to check whether it's been better, right? So firstly, if it's been visited, we should continue. Secondly, we need to check we should only push something in the priority queue if we found a better distance for it, right? So if, for example, if our distance for V is currently is worse than the distance from U plus the edge weight, and I don't know, I'll just call this edge UI. I should probably add edge weights, but whatever, it doesn't really matter. .node, .weight. I don't really care. And so as we do this, basically if it's greater than the distance of U plus the weight of the adjacency list, then we should do two things. We should firstly update our distance to the new best distance. And then we should push it into the queue with the added distance. So does anyone have any questions about this implementation? I went through it pretty quickly. Crucially, it's slightly longer than the BFS implementation because we have to do this thing with sorting. But yeah, it's crucial. It's pretty much the same thing. So. Yeah, you guys can have pizza now. We'll resume after you guys have had your share. Okay, fine. Oh my goodness.
Just to be clear, guys, after the food break, there will be more challenge problems, but you can get food if you want.
Yeah, anyone who didn't sign this attendance form, could you guys sign it just so we can get food to you guys? Yeah, I'll put them up. Yeah. So whoever's gluten free, there's gluten free pizza here. So hey, you're hand sanitizer? Do we have?
There are toilets, I think, on this floor in the back end.
Yeah, you probably wash Are you the gluten-free one?
I
Oh,
believe
yeah.
this is the one. That's the only one that has like the crust that's completely different.
Should I put on the tape?
No, you can
Have
just
your-
eat it.
have your
Yeah.
fair share.
Everyone like has.
You missed out.
Susan, you sure you don't want to take a more active role in this? Yup.
She asked if she could join my team for So I think you should take care of this.
And you will,
She hasn't spoken to you.
yes, great work from you, I guess.
Guess who she is.
Yup. Alright, have fun. Yeah, okay. Yeah, so am I. It's like very reasonable. Yeah.
Take your names off this. It's over for me, but
True for all of us. Did you like underestimate the capacity for people to stalk you? Very door.
have you heard about what we did?
No?
I'll tell you after.
Yeah.
Hi everyone. We might get started with the remaining portion of the workshop. Hello everyone. We might get started with the remaining part of the workshop. So I guess we'll continue. Guess like you guys can stand around. Hi. Hello. Hi. Oh, bye. Bye. Goodbye. Stay away. Yeah.
Are the slides for this going to be released?
Yeah.
Where?
With Discord, we'll put on Discord. We also put on like the website. The website. All right, so we'll get started. Just to finish up with Dijkstra's algorithm, we do have like to discuss some of the shortcomings of Dijkstra. So if you remember like how we derived Dijkstra's algorithm, like as I guess like as a refresher, how did we derive it? We took basically these edges with weights. So we took these edges with weights and we split them into like unweighted edges, right? So there's one key problem with this scenario, and that's when the weight is negative, right? When the weight's negative, you can't really split up the graph into a bunch of negative edges, right? We can't split up into a bunch of ones which sum up to a negative number. So in this case, we cannot actually construct our BFS representation. And like, actually in this case, Dijkstra doesn't work. The greedy claim fails, right? So the closest node's distance isn't always the best. So if like, for example, you visit 3, and with a distance of 2, and that's the smallest node, you can't be guaranteed that there's no guarantee that you can't find a better path later on, which takes a negative edge and improves that distance, right? So the greedy claim of Dijkstra fails. So we have to actually continually update all our nodes. So the modification to Dijkstra in order to do this is actually like update every node, right? All the time. And so this is actually like Bellman Ford, so we won't worry about that. It's a different algorithm. Can anyone think of any other potential issues with the algorithm correctness? I put this as an open question because I couldn't come up with any off the top of my head. But like, there's probably some more issues. Anyway, we'll move on to looking at some tricks. So these are some tricks which I will actually expect to like maybe come up in the exam. Like it's fairly feasible that these will come up. There are a number of there are several tricks some more interesting than others. What I'll cover is basically 3 which I think will have a possibility of actually coming up in the exam. And so this one was inspired by actually when I sat the supplementary exam, I think last term or something, or this term, start of this term. I actually got this problem, a very similar version of this problem in the exam. So it's very good if you guys can solve this problem. So this problem is called crossing the river. And in this problem, you're attempting to cross a river, and it's modeled as a grid of n by n cells. Sure. And basically the idea is you can start anywhere along the upstream shore, which is the cells in row 1. So, and you have to finish anywhere along the downstream shore, which is cells in row n. So basically, yep. Yeah, I'll share the slides, yeah. Also, I think there's a stream going right now. You can watch the stream after as well. So basically, you're trying to cross a river, and it's an n by n grid, and you can start anywhere along row 1, and you can finish anywhere along row n. And basically what you're allowed to do is you're allowed to move in any of the 4 cardinal directions, right? And it takes 1 second to move from a cell to an adjacent cell. So you may already be I guess thinking about how do we model the grid as a graph maybe, not sure. And so actually we're going to improve, make the problem a bit harder. So to make the problem marginally more challenging, there are actually k blocked cells which you can't pass through. Right? And you can't actually start on those cells either. So they're blocked off, you can't go through them, you can't visit them, and you also can't start on them. And the question is, given this map of the river, so you're given I guess the n by n grid with k blocked cells, and you want to determine the shortest time to cross it, given that you can start anywhere on the first row and finish anywhere on the last row. So what does this look like? In this case, I don't think I generated a square grid, but you can see the point. I just add an extra row, it doesn't really matter. So in this particular example, you can start anywhere along this top, and you can finish anywhere along this bottom, right? And so maybe one path you could do is start at 1, and then takes 1 second to move here, 1 second, 1 second, 1 second, and that gives a total path length of 4, right? But you can do a bit better. And you can't do better by going to 3. If you start at 3, you screw yourself, right? But you can do better by starting at 5. In this case, you can just finish the path in 3, or the grid in 3. Does this make sense to everyone? Does the problem make sense? The problem is basically you can start anywhere along here and finish anywhere along here, save for the blocked cells, and then you need to get from the top to the bottom in the minimum distance. And so I guess if there was just a single point to start at, we could just BFS from that single point, right? But in this case, we've actually got multiple potential starting points, right? For example, say we were told we can only start at 1, right? Then the problem is relatively simple. This grid is basically modeled as a graph, right? An implicit graph, I guess you could call it. And then say we said we knew we were going to start at 1, then it's very simple. We can just run a BFS along this graph, right? We make sure that we don't visit any edges, nodes which are blocked. And then we just BFS, and that gives us, since this graph is unweighted, it gives us the, I guess shortest path from 1 to anywhere. We just check the first time we reach any cell on the bottom is the shortest path to the bottom. Yeah. So in this specific scenario, we are able to, start a BFS at 1. But in the actual problem, we actually could potentially start any of these locations. How do we do this? One way that I could see myself doing this is I basically start BFS run 1, I run it, and then I reset. I start BFS at 3, I run it. I basically try each of the cells or each of the things along the top row, and then I'll run a BFS independently for each one, and then minimum over all of those BFSs. So what do you think the time complexity of this solution is? Anyone have any ideas? So just to recap what my solution for this problem is I know that if I start at a specific location, I can just run BFS from that source vertex and get the shortest path to any node on the bottom, right? The first time I reach a node at the bottom row is the shortest path to the bottom. So what I can do is basically I start a BFS at 1, and I see what that gives me as the shortest path. Then I will repeat for 3, for 4, and for 5. And then I'll take the minimum over all of those BFSs. So I'm trying every starting position, and for each one, I'm finding what's the minimum like path length, I guess. And so like what would the time complexity of this solution be? Hmm? I'm trying every single one of them. Yeah, pretty much, right? Like the time complexity of this solution, let's say there are I guess like this is an n by n grid, so there are n squared nodes, and there are like n nodes that we have to try from the top. This would be n times like n squared plus, or like n squared plus some number of edges, which is on proportion to n squared. So you're roughly going to get an O of n cubed time complexity. Does everyone understand the complexity calculation? I can like do it, I guess. So basically, the idea is, okay, these boards aren't going to move, are they? Okay, so the idea behind the time complexity calculation is, okay, it might be extremely difficult for some of you guys to see, but the idea is, this is an n by n grid, right? And then how many nodes are there on this n by n grid? Roughly n squared, right? Because there's a node for every grid point, and there are n squared grid points, right? How many edges are there? Well, basically, each node has 4 edges coming out of it, roughly. So it's like roughly order n squared as well, right? Each node has some like constant number of edges coming off it. Like sometimes it's 4, sometimes it's 3, sometimes 2. It doesn't really matter. Yep. Is it n squared? Like, I believe it's not, right? As in like the number of nodes or the number of edges? Oh, the number of nodes? Like it is n squared. But like I don't really care because I'm just doing a rough time. But like it is actually n squared in this case. For example, for edges, it's not it's n squared with some constant multiple, right? But we know we discard constants when we do time complexity. Yep. Why is it n squared? Like each, if you can think about it, like each node has like 4 edges coming off it, right? And so basically, there's at most 4 n squared edges. Yeah. Obviously, by doing that, you're double counting some edges. You're doing some other stuff. Like it's probably on the order of like 2n squared plus minus something. I don't really care, right? I just want to know that it's roughly proportional to n squared. Yeah, with some constant factor. And so the number of nodes plus edges, if we were to run a single BFS, would be O of number of nodes, n squared, roughly, and then plus the number of edges, n squared, roughly. So this is basically order n squared. Yeah? Because we just disregard all the constant factors. So it's O of n squared to run a single BFS on this grid. And so if we're trying all of the positions on the top row, and then for each one we're going to run a BFS, it will be order n times, for each one we're going to run a BFS, n squared, so this will be order n cubed. Does anyone have any questions about this time complexity? Yeah, sure. So basically, the idea is we have n squared nodes on the graph, and also n squared edges, roughly. Yeah? So we know that the BFS complexity is O of V plus E, right? V is the number of vertices, and E is the number of edges. So in terms of n, that looks like roughly order n squared, right? There's roughly n squared vertices, and there's roughly n squared edges. Yeah? So on net, it's roughly going to be, I'm saying roughly a lot, because that's time complexity, I guess. The BFS is basically going to be order n squared. Does that make sense?
That should be 2 times n.
Yes, exactly, right? But like when we look at time complexity, we disregard all the constants. So if there's like, for example, if it's 2n squared, that basically grows just as fast as n squared, right? It's like the same complexity class. The way that we think about time complexity is like I don't know, it's like roughly how does it grow in relation to n? Like what function of n does it grow with, right? And then so we don't really care about things like constants because, for example, n cubed will always be slower than an n squared algorithm for a large enough n, right? So we don't really care about constants; they'll always get outpaced by the growth of n. Yeah. So roughly n squared for BFS, and then so we're going to loop through each of the possible starting locations. There are n of them, and then for each one we're going to run a BFS. That's n times n squared. Yeah. So n cubed on net. Does that make sense? Does the time complexity make sense so far? Yeah, sure. So now that we've figured out the time complexity of this, let's say I wanted to do better than this. I wanted to just find an n squared algorithm. Let's say n cubed was like not sufficient. The way that we can actually do this is we can just construct a dummy node 0, which connects to all the nodes at the top with weight 0. So basically what we're going to do is we're going to create like a new node here, which is like a fake node, and then that's going to connect to all of the things on the top, and the edge weight of that will be 0. Yeah? Equivalently, we can just add all the top row vertices to our BFS queue to begin with. And basically, the answer is just the first time that we hit a vertex on the bottom. Why is this true? Like, basically what we're doing is we're just creating a dummy node here, and the distance to all of these will be the same. And so what we're doing is whatever we basically like create a node where we have a choice of like which one to start at. And then so if we just run BFS from that one singular starting node, which connects to all of the things along the top with weight 0, we win, right? Does this make sense? Like, we're basically creating an option for our algorithm itself to make a choice, like which one should we start at. So we create like this source node, which is like a node 0, doesn't really do anything. And then we connect it to everything on the top with, I guess, like you could make it weight 1, you could make it weight 0, doesn't really matter. And then at the end, it's either the shortest path from starting from here all the way to the bottom, in which case that is like, that's like if you link these with weight 0, or if you link these with weight 1, it will just be like you start from here, you BFS, and it's like the length of the thing minus 1, right? Because you made this initial choice. Does this make sense to everyone? Yep. Yeah. The point of doing that is like you just have to run a single BFS now. So you know how previously we had to like run n BFSs? Yeah. Now we just create a singular node, which like passes itself. We create like a singular node, and this like connects to every single one of the top things, and we just BFS from this singular node. So we just do one iteration of BFS. Yeah. And so with a single iteration of BFS, where we've already accounted for all the source nodes. And so this trick actually works for general graphs too. So not just grids. If you have a bunch of source nodes that you want to start at, you can just create a dummy node and then link those all to the source node, right? Or to all the sources, and then have your BFS algorithm itself make the choice. Yep. A graph? Yeah. So that's a good question. So this is maybe something which you guys might have covered. But for example, first thing I want to do is provide a labeling for these vertices, and maybe like I would 0 index, and I'd say, okay, like if I am at 1, 1, I'll be like node. I'll call my node like 1, I guess. And like you can like create an index using just some maths, like try to figure out given a position, what index should it be. This is like a fairly straightforward procedure. Like I think it's like your row times some constant or times your I guess like your row number times the number of columns there are plus like your column number or something. That's sufficient. So basically you're labeling all the vertices like that. And then the second thing you want to do is you want to basically say, I will connect to all of the things to any node which is like directly above me. Yeah? And then so for example, if I was at like, I don't know, this point, like what coordinate is this? Like, I don't know, 1, 2 or something. I don't know. I'll connect like 2, 1, right? I'll connect like 2, 2, whatever. 3, 2. 3, 2, I'll connect 3, 2 to like, I guess like 3, 2, 2, and then like 3, 1, 3, 3, and then like, I guess like 4, 2. So you like basically figure out all those positions for each node. That takes like O of 1 time, technically O of 4, doesn't really matter. And then like you construct the graph like that. Yep. Yeah, that like how would you turn a grid into a graph? Yeah. This is something which you should have covered in the course, I believe. Yeah, like grids. Like grids as graphs will probably be in the exam. Like this is like actually something I got. Like this is like a question that I got. So yeah. Like okay, like I haven't emphasized it enough. Like this is like I did this question, right? So yeah, okay. So the next trick I guess I want to look at is this thing called sorry. I think it's the last implementation question. Oh, okay, sure. Okay. Yeah, okay. And so now let me take the same question and let me add like a spin on it, right? So imagine the previous question now, but each non-block cell also has a current. right? Because we're in a river after all. And this current points in one of the 4 cardinal directions. So either north, south, east, or west. And so at any vertex or at any grid point, you can either choose to turn in any of the non-current directions, which will take 1 second, or you can choose to ride the current. And if you ride the current, it'll take no seconds. So what's the shortest time to cross from one side to the other is now the question. And I guess I'll spoil it for you because we want to like be a bit quicker. I think Matthew has some interesting problems to discuss with you guys. But for this particular problem with graph, we can basically model this as like, instead of just a graph where all the edges are cost 1, we can model the graph as a graph where some of the nodes are cost 0, right? Some of the edges are cost 0. For example, say the current in 6 was pointing right, the weight from 6 to 7 would be 0, right? And then likewise, I guess like if it was pointing down, this weight would be 0. So for each, so when you construct the graph, basically, you also want to check the current direction. And then so like for each, wherever, when like basically, if this node current points like east, you would change like this east edge to be weight 0. And then the rest of the edges would still be weight 1. Yep. Yeah, you can Dijkstra it, right? Like, excellent work, right? So everyone understands, like, you can, like, do the same thing where you create, like, the source vertex, you add it to everything with weight 0, and you Dijkstra from that single point, right? But there's, like, a bit of a faster way that we can do it. Since each edge weight is either 0 or 1, the priority queue looks like a bunch of nodes where it's, like, the same distance away, and a bunch of nodes where it's, like, 1 distance away, right? If you think about what our queue will look like, or our priority queue will look like when we perform Dijkstra. So it'll look like all the nearer nodes, which is like all the nodes we can reach with cost 0, and then all the nodes we can reach without, like with cost +1, right? So what we can actually do is we can use something called a deck, or we can just use a single linked list, right? So in C, you would use a list, linked list, and basically, every time we peek at you through an edge of 0, we'll just put it at the front of the linked list, right? Insert at the front of the linked list, and then otherwise, if we peek at it through an edge of 1, it should go like after. So we should insert it at the back. Does this make sense? Yep. Deck is like a linked list, pretty much. Yeah. Yeah, W linked list. Yeah. It's like a linked list. It's like a doubly and like linked list, I guess. And yeah, you store the one next and the one before. And so you can like insert at the front and you can also insert at the end. Like you store a head and a tail and then whatever, right? It's very doable. And so both these operations are O of 1, so you can actually do a bit better than just log. You can actually just do it in n squared. You don't need this extra log factor. From using Dijkstra, you can just do it in n squared. Yeah. And I guess the last thing I want to do is cover this problem, which I did spend some time writing. So this problem is called minimize maximum miseries. And the problem is, miserable Momo must make a mandatory midnight march from mansion 1 to mansion n through a misty metropolis. And this metropolis is modeled as n mansions and m meandering motorways. And each motorway has a non-negative misery measure, right? So basically, it's like a graph, okay, whatever. Okay, like, yeah, whatever. So when Momo moves along a motorway, the motorway's misery measure melds into the march's misery. Momo is not measuring the mere sum of miseries. They mind only the most monstrous moment, which is the maximum misery measure amongst motorways marched on. Yeah? Okay, like, basically the problem is like, yeah, like the problem is like, you're given a graph, right? And each edge has a weight. And your job is basically get from 1 to n, so that the maximum weight that you travel on is minimized, right? And the questions like do this. Like, you must make the march's maximum misery as minimal as mathematically manageable. Okay, like, someone needs to appreciate this problem statement. Okay, true? Okay, like, it was like 30 minutes, and it was like at 11 something, or 12 something. Shit, I forgot what time it was. Might have been, I don't know. But yeah, I was pretty out of it by this point, so yeah. So, basically, the idea of this problem is like, instead of just looking at the sum of the weights, you want to, the path is scored by the maximum weight that you traverse on, right? So, like, you know how Dijkstra like does all of its pathing based on like the sum of weights, right? And so now we get this problem where our path is scored on the maximum weight that we travel on. And so how do we do this? Well, it turns out we can just use Dijkstra the same way. Instead of just having a sum, we just replace it with a max. And so, like, why is this true? Like, it's the exact same as normal Dijkstra. Instead of updating the distance as you add the weight of the edge, you just max it. Now, why is this true? Well, basically, Dijkstra claims that the smallest distance node is accurate and it's the best place to expand, right? And so we should visit it and we should cement its value in history, right? And this is even true. This is still true. Even for this cost function, which is max. And the reason why is because this cost function is something called like monotonically increasing. So as we move along the path, the score can never decrease, right? Our score for our path can never decrease as we move along the path and as we expand more. So Dijkstra can still be confident that the best distance node is, like, the current best distance node is the best that we're ever going to get for it, right? Like, every other node has a cost at least as bad as your current best, right? By definition of Dijkstra. You're never going to find a path which will make your current node better. So you should just visit it. Does this make sense to everyone? Yeah, I was like pretty fast explaining that. Monotonically increasing means as you expand the path, the cost of the path never gets better. So like it never decreases, right? So for example, in typical Dijkstra, you always add positive numbers. So your path length always increases as you expand. In this problem, you always max it with the current thing. So like if your current thing is bigger, it will stay the same. If you see a worse edge, your score will increase by that edge, right? So in both situations, as we expand the path, the cost of that path does not ever decrease. And so we can use Dijkstra for this as well. And I'm pretty sure like this also extends to more complex cost functions like delays and windows and nodes. Pretty sure like an assignment that you guys have right now or something has like time durations at nodes or something. Yeah, you can like do this.
By the way, for this problem, like that problem, there are like many other solutions as well. You can use binary search in a DFS. You can use DSU if you've learned that. This is just one solution. Okay, so we finally gotten to my section a bit late. These are challenge problems. The first few aren't that challenging, so I'll leave you guys plenty of time to solve it and tell me what you think the solution is. Okay, so the first problem, and of course I flavored all these problems as Austin did, is down under. So Agartha needs your help. Despite living in a mythical kingdom with UFO technology and raw milk, the Agarthans have not figured out how to build a highway. Their road network consists of N sacred chambers and M bidirectional edges between those chambers. The High Priest has ordered you to ensure that there exists a route connecting any two chambers, and you want to know what is the minimum number of new tunnels you need to add to achieve this. So in graph world, this means that you have some graph, just a simple graph, and it is disconnected. So not all the nodes belong in the same component. And you want to know what is the minimum number of edges I could add to this graph so that all the nodes belong to the same component. Yes? The total number of nodes? Yes, you're given the total number of nodes, edges, and what the edges are. It's your job to find out the answer from there. Yes. Mm-hmm. Yep. Uh-huh. Yep. So the idea is you start from one node, you find the component that it, like all the nodes it can reach, right? And then if it can't reach all the nodes, you know you need to add some edges, right? The question is just like how many edges specifically, or what is the minimum number of edges you have to add? So just for example, in this case, what do you think it would be? What's the minimum number of edges I'd have to add to make the whole graph connected? 2, right? So, for example, like that. So any ideas how we could do this in code? Yep. So do a minimum spanning tree, is that right? Yep. Okay, yep. Uh-huh.
But in that example, the startup one has like a 3. So when you subtract it, you actually
I think there are some problems with the minimum spanning tree, especially like because to do the minimum spanning tree, right, you need like you need some set of edges to start with, right, to add to your minimum spanning tree. And if you just wipe all the edges, you know, like are you going to make a complete graph, or it's a bit unclear. Let's go back to the original graph because I think that'll help. So the original graph did not have those added edges. What sort of property do you think in this original graph determines what our answer will be, right? So in this case, there are how many components? 3 components, and you need how many edges? So what do you think the relationship is between the number of components? Minus 1, right? Yeah. Okay, that's exactly right. So the thing that determines our answer is really like how many components are there. So you can just think of every component as one node, and if that's the case, it's just the number of components minus 1. So now that we know that, how do we count the number of components in a graph of connecting components? Any ideas? How do we count the number of connecting components? I mean, from early in the lecture, if we start at one node, we can find all the nodes in its connecting component. What algorithms would we use to do that? I think you have the right idea, which is that we use DFS to sort of mark all the nodes that are in the same component. Is that right? Yep. So if we do that, you can think of what it's going to look like in code. I mean, it's sort of like I'm going to loop through all the nodes. I'm going to DFS from the node. And if I've already seen the node, then I can skip it. Else I know that I have one more component. So using DFS, we can just simply count how many components we have. And then once that's done, we can subtract 1, and that would be our answer. So, and last thing, if we just did that using DFS, what would our final time complexity be for this problem if we had n nodes at the start? Yeah, I'll do B, okay? Yeah, the number of vertices plus the number of edges, right? N plus m. We'll do one more problem. I had one more problem after this plan, but I think we only have time for this last one. So, very similar problem. We are in Agatha again, but this time the edges are directed. So all the tunnels can only be traversed in a single direction, and the high priest tells you exactly which direction they can be traveled in. Your question is, you need to answer to the high priest, can I get from any node to any other node in this graph? So for example, our new graph might look like this. So it's like just like the old graph, except now the edges are directed. And the question is, in this graph, can we get from any node to any other node? If we start at any node, is it guaranteed that we can reach every other node? No, we cannot. And why is that? Yeah. If we start at 4, we're stuck. We can't get to any of the other nodes. So does anyone have any ideas about how we could check whether we can get? Yep. Yes, DFS from every node, right? Yeah. So the first solution is we can just simply run DFS from every single node, check if we can reach every other node, and if we can, we output yes, else we output no. I think I don't have time to let you guys think, but the the full solution basically is that we can limit the number of DFSs we do from doing n DFSs to only doing 2 DFSs. And the reason that is that if we have a node U such that you can reach every node and every node can reach you, then every node can reach every other node, right? And that's because any node A can go to U and then go to B. So U sort of acts as like a middle node between every pair of nodes. To check whether that's true, we can simply run a DFS. Yeah, I don't know. Yeah, sure. We can run a DFS, and then we can reverse the edges, and then run a second DFS. If all those return true for all the nodes, then we know our answer is yes, else our answer is no. We're getting kicked out of here because there's a class. Thank you guys all for coming. Hope you guys learned a lot. And please come to more of the workshops.
Thanks, everyone.
Good job, guys.
Okay, like
This
we
slide
pass.
is available in the chat, right?
Yeah, slides will be up.
In the forum?
We can ask Henry to put them up in the forums. Yeah, sure.
But they'll be on our website otherwise.
Which website is it?
UNSWCPMSoc.com.
Bye, everyone.
I'm just worried now. Sorry.
That's fine, don't worry. That's all the electronics for this.